In this video, we're going to talk about how to calculate the change in enthalpy of reaction for a physical or chemical process using standard enthalpies of formation. Now, previously we talked about how one could do this using calorimetry or using bond enthalpy. Today we'll focus on using enthalpies of formation, and in the next video we'll talk about Hess's law, which justifies some of the things we're going to be doing with our equations today. Now, the standard enthalpy of formation, symbolized delta HF with that little circle, is the enthalpy change for a reaction in which 1 mole of a pure substance is formed from free elements in their most stable states under standard condition. That little circle or degree symbol, which we sometimes call naught, indicates that the reaction is taking place under the standard conditions, 1 atmosphere and 273.15 Kelvin, or 0 degrees Celsius. The sign convention for the standard enthalpy of formation is the same as the sign conventions for our other change in enthalpy reactions. If the standard enthalpy of formation is less than 0, the reaction is exothermic. If it's greater than 0, the reaction is endothermic. Standard enthalpy of formation is different from the bond enthalpy we talked about in the previous video. However, there are some similarities that make these two things easy to confuse. The bond enthalpy is the enthalpy change when 1 mole of bonds is broken, and we can use these bond enthalpies to calculate the energy change if we imagine we're vaporizing the substance and breaking the bonds and then forming new ones. Remember that bond enthalpy is only applicable to compounds in their gaseous state. With standard enthalpy of formation, however, we're looking at how much energy it would take to form a compound from scratch. And we can get the values for standard enthalpy of formation from a table. Standard enthalpy of formation is reported in kilojoules per mole. Now take a look at this table and notice that the standard enthalpy of formation is usually negative, and this is because forming bonds is typically an exothermic process, but there are some exceptions. The enthalpy of formation will vary depending on the state of the compound and whether it's solid, liquid, or gas. Before we go too much further, we need to talk about standard states. Heat of formation equations are always written so that the reactants, in other words, the elements that form the compound we're looking at, are in their standard states. This means the form they would naturally be in at standard temperature and pressure. Many elements are monoatomic, that means single atoms in their natural state. For example, noble gases and metals, to name a few. However, some elements are diatomic in their most stable states. The diatomic elements are iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, and fluorine. And there are a couple of ways to remember these. I have no bright or clever friends, or Brinkelhoff. And no, I do not know where that came from, but it's a thing. Now, phosphorus usually exists in nature as P4, and the standard state form of carbon is graphite. So you'll sometimes see graphite actually written after carbon to indicate that it is the standard state. The enthalpy of formation of any element in its standard state is 0, and this includes diatomic elements, graphite, phosphorus, etc. Now let's talk about how to write an enthalpy of formation equation. Let's consider the following reaction. 1/2 nitrogen plus oxygen yields nitrogen dioxide. As you can see, the equation is scaled so that there is 1 mole of product. There's a coefficient of 1/2 in front of the nitrogen, and this is not a mistake. The coefficients in front of reactants must be scaled so there is 1 mole of the product. In this case, it's 1 mole of nitrogen dioxide. Let's look at another example. Consider the compound calcium phosphate. Notice that the enthalpy of formation equation shows how this compound is built from calcium, phosphorus, and oxygen, all in their standard states. We can see that the standard heat of formation is negative, so this reaction is exothermic. Notice how the equation has been written for 1 mole of product, and this explains the fractional coefficient in front of the phosphorus. Now let's do an example problem. We're asked to write a balanced chemical equation corresponding to the standard enthalpy of formation of magnesium carbonate. So first, let's break this down into its elements and put it into elemental form. Magnesium is monoatomic and it is solid, and we're going to add carbon. And the standard state of carbon is graphite, which is a solid. We will add oxygen gas. Oxygen is diatomic to form our magnesium carbonate. We're going to balance this just as we would a regular equation, and this is what we get with our coefficients: 2 magnesium, 2 carbon, 3 oxygen, and 2 magnesium carbonate. Now we have to balance it as an enthalpy of formation equation for 1 mole of product. And this means we're going to have to divide everything by 2, which is the coefficient on magnesium carbonate. And we end up with 1 mole of magnesium, 1 mole of graphite, 3/2 mole of oxygen, and 1 mole of magnesium carbonate. And you see we have a coefficient of 3/2 in front of the oxygen, and that is correct for this type of enthalpy of formation equation. Now, to determine the enthalpy of formation, that's something that is done experimentally, typically through calorimetry. If we know the enthalpies of formation of the reactants and products in a reaction, we can determine the change in enthalpy for the reaction. And here is how we do that. The first thing we'll do is make sure the equation's balanced. Then we're going to go to a table and look up the enthalpies of formation of the products and the reactants. We're going to use this equation. We're going to subtract the sum of the standard heats of formation for the reactants from the sum of the standard heats of formation of the products. And we have to remember to include the stoichiometric coefficients in our calculations. Notice that this equation looks very similar to the bond enthalpy equation we used for bond enthalpy, but it's very different and it should not be confused with it. When we're using the heat of formation equation, we're adding the heats of formation of the products, and those are usually bonds forming and therefore exothermic, but not always. And we're going to subtract the heats of formation of the reactants. And we subtract these because we're effectively running the formation of the reactants in reverse. The reactants essentially have to break down before they can form new molecules. So here's an example. We're going to calculate the standard enthalpy of reaction for the combustion of glucose. And to do this, we're going to take the sum of our standard enthalpies of formation for the products and subtract the standard enthalpies of formation for the reactants. So we'll look up the values in a table, and we can either put them right into the equation like this, accounting for the stoichiometry, or we could put them in a table like this. Now, this sometimes looks like it takes a little bit of extra work, but it may help minimize some of the mistakes. One of the mistakes I see most often is people forget to distribute that minus sign that's between the products and reactants. And if you put things in a table, you're less likely to make that mistake. So let's go ahead and do this. And I make sure to take my coefficients into account. I'm going to take the standard heats of formation for my products and subtract the standard heats of formation for my reactants. And I get the same thing I got doing it the equation way. Negative 2803 kilojoules per mole. This reaction is exothermic. So to summarize, you should now be able to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation, and you need to know that tables of standard enthalpies of formation can be used to do this, and this is the equation.